Assalamualaikum dear students, I hope you all are fine and in the best conditions of your health. So in today's lecture we shall study about comparison of alkane, alkenes and alkynes. The key concepts which we shall discuss in this lecture are a comparison of structure and reactivity of alkanes, alkenes and alkynes. So before going to our concerned topic, it's very important to know what are the hydrocarbons, right? Hydrocarbons are simplest organic compounds which contain only the elements of carbon and hydrogen. So even though they are composed of only two types of atoms, that's carbon and hydrogen, they have a variety of hydrocarbons. Why hydrocarbons are a variety of compounds? Because of following reason, right? So these hydrocarbons, they can consist of varying length of chains. They can consist of varying length of branch chains. They can have varying lengths of rings or combination of these structures, right? So by combination of carbon and hydrogen in the form of chains, in the form of branch chains, in the form of rings, or a combination of structures that have both the chains, branch chains and ring system. So you can just imagine that how much variation we can get from these simple hydrocarbons. Also, these hydrocarbons differ in the type of bonds present in the structure. So hydrocarbon can have all carbon-carbon single bonds, it can have carbon-carbon single bond as well as double bond, it can have carbon-carbon single, double and triple bond as well, right? So because of these combinations, the hydrocarbons have a wide variety of compounds. So most of the hydrocarbons, they are found in plants, animals, they're fossils. Some have also been prepared in the laboratory. So normally the hydrocarbons are used in everyday life as fuels or as plastics. So among fuels, we can have natural gas, we can have ethylene, propane, butane, and principal components of gasoline. Furthermore, we have diesel fuel and heating oil. So all of these are hydrocarbons. Similarly, the plastics which are normally used, such as polyethylene, polypropylene and polystyrene, these plastics are also hydrocarbons, right? So majorly hydrocarbons, if you are wondering how hydrocarbons are used in everyday life, so the hydrocarbons are normally used either as fuels or they are used as plastics, right? So we can distinguish the hydrocarbons on the basis of difference in bonding between the two atoms, right? So if all the bonds are single, then we say that hydrocarbon is saturated, but if there is presence of a double or triple bond, we say the hydrocarbon is unsaturated, right? So depending on the difference in bonding, whether there is a single bond, whether we have a double bond or triple bond, so the difference in the bonding result in difference in geometries and hybridization of the carbon orbital, right? So because the difference in geometry, the reactivity of these hydrocarbons is also different. So let's consider firstly the alkanes. So alkanes are saturated hydrocarbons. So why they are saturated? Because alkanes have all carbon-carbon single bonds, right? So here we are mentioning alkanes which are open chain as well as cyclic alkanes, right? So they are considered saturated because all the covalent bond between carbon atoms is single. So in alkanes, each carbon has an sp3 hybridization, and each carbon is bonded to 4 other atoms, right? And because the hybridization is sp3, as you know, that bond angle is close to 109.5 and giving these hydrocarbon a zigzag shape. In case of cycloalkanes, when you are considering cyclopropane and cyclobutane, the sp3 hybridization is present, however the bond angle is reduced a lot. So you have studied about the concept of ring strain. So in ring strain, the angle strain of the cyclopropane and cyclobutane that causes the bond, this bond angle to be reduced to a larger extent, right? And because of the same reason, the cycloalkanes are highly unstable, right? Otherwise, in all of the cycloalkanes and in alkanes, the bond angle is close to 109.5, which is the ideal angle for sp3 hybridization. So all alkanes, they are composed of carbon and hydrogens because they are hydrocarbons. All alkanes have similar bonds, similar structures, similar formula, And in case if you're wondering about non-cyclic alkanes, so they have general formula of CnH2n plus 2. In case of cycloalkanes, the formula is CnH2n, right? So why it's not CnH2n plus 2? Because when you are forming cycloalkane from an alkane, you have to remove 2 hydrogens from the alkanes in order to close the ring, right? So although we are missing 2 hydrogens from cycloalkanes, but they are considered saturated on the basis because all the bonds between carbon and carbon are single, right? So also you should know that the number of carbon atoms in an alkane has low limit. So you can even have a alkane that has thousands of number of carbons, right? So there is no limit on the number of carbon atoms that are present in the alkane. Also, you should know in general that as the number of atoms in a molecule increases, right? So with increase in number of atoms in a molecule, the intermolecular forces become stronger, right? And because of the intermolecular forces, the physical properties of a molecule differ, right? So if you have stronger intermolecular force of attraction, then in such cases the melting point and boiling point will be higher. And in case if the intermolecular forces are weaker, then the melting point and boiling point will be lower, right? The physical properties are affected by intermolecular force of attraction, and the intermolecular force of attraction is dependent on the number of atoms, right? Greater the number of atoms, stronger will be the intermolecular force of attraction, and different physical properties will be encountered. So you can change the physical and chemical properties of an alkane by changing the number of carbon and hydrogen in a molecule. Now let's consider about the reactivity. Alkanes are relatively stable molecules, but if you provide heat or light, then in the presence of heat or light, these molecules are activated and they undergo reactions. And normally when we carry out the reaction of alkanes, these involve the breakage of carbon-carbon or carbon-hydrogen bond, right? So since alkanes are saturated, they have all the bonds single, so we cannot add anything on this bond. The only thing we can do is we can break the bond, and either we can carry out an elimination reaction or we can carry out a substitution reaction, right? So alkanes are relatively stable molecules, but if you provide heat or light, then we can activate these alkanes to undergo reaction. So normal type of reactions which alkanes undergo are 3. So alkanes either undergo combustion reactions, or they undergo pyrolysis, or they undergo substitution reaction, right? So combustion reaction involves burning the alkane in presence of excess of oxygen, right? So if an alkane, for example, we have a methane and we are heating it in presence of excess of oxygen, then this alkane breaks down into carbon dioxide and water, and the reaction is highly exothermic, so a large amount of heat is produced. So this reaction is used in our kitchens, and this is the same reason why alkanes are used as fuel, because when they burn in presence of excess of oxygen, they produce a large amount of heat which can be used for cooking or other purposes. However, if the oxygen is not present in excess, so if there is an environment in which oxygen is insufficient, then instead of formation of carbon dioxide, we have carbon monoxide here, right? So when you are burning an alkane in presence of insufficient amount of oxygen, then we get carbon monoxide plus water. So carbon monoxide is an air pollutant, and since there's an air pollutant, that causes too much buildup of carbon monoxide in the atmosphere, right? And that is responsible for pollution of air, right? So this is also responsible for suffocation of people. So whenever there is carbon monoxide in the environment, so you feel difficulty in breathing. So combustion of alkanes is a highly exothermic process. So alkanes are excellent fuels. For example, we have mentioned here the example of methane in the previous slide. Similarly, butane is used in camping stoves. The cylinders which you use in your homes is has normally the butane as the fuel. Also the lighters, the cigarette lighters or the stove lighters which we use, this is normally composed of butane. Gasoline is a liquid mixture of continuous and branch chain alkanes, and each has 5 to 9 carbons. Plus we also add some additives to improve the performance of this fuel, right? So whenever someone asks you what's gasoline, so gasoline is a liquid mixture of straight chain and branch chain hydrocarbons, and these alkanes, whether they are straight chain or branch chain, they have number of carbon which range from 5 to 9, and also we add some additives to improve the performance of this gasoline, right? So we have then pyrolysis. So pyrolysis is a process in which we decompose the hydrocarbon into elements, right? So there is a difference in combustion and pyrolysis. In combustion, we convert the hydrocarbon into carbon dioxide and water, while in case of pyrolysis, we carry out the heating of hydrocarbon at very high temperature and we convert the hydrocarbon into its element. So we can convert the methane into carbon and hydrogen, right? For this purpose, we use temperature up to 2000 or higher. So substitution reaction is a typical reaction of alkane. So we cannot add anything on an alkane, but we can carry out the substitution of alkanes, right? So in this reaction, what we do is that we replace one or more of the alkane's hydrogen with some other atom or group of atoms, right? So one thing important you should know, that in substitution reactions, the carbon-carbon bonds are not broken and the hybridization of the carbon is not changed. So hybridization will remain the same. The hybridization of the alkane and the product will be the same. So both will have sp3 hybridization, right? So for example, here we have an ethane. So ethane on reaction with chlorine, presence of hydrolyte. So that will result in formation of chloroethane, like this. So you can see that we have replaced this hydrogen with this chlorine, and the hybridization of the carbon remains sp3. Also, we have not broken any bond between carbon and carbon. So substitution reaction does not involve breakage of carbon-carbon bonds, and it also does not involve formation of change in hybridization, right? So next we have unsaturated hydrocarbons. Organic compounds that can contain one or more double bond or triple bond between carbon atoms are called unsaturated, right? So you might have heard of unsaturated fats. So unsaturated fats are actually long chain of carboxylic acids that have at least one double bond between carbon and carbon, right? So double bond or a triple bond, you should know that they are formed by parallel overlap of the p orbitals, right? And the p orbitals that form the double or triple bond, they are unhybrid orbitals. You should also remember that. Further, you should also remember that a double bond has one sigma bond and a pi bond, and sigma bond is stronger, pi bond is weaker. A triple bond has one sigma bond and two pi bonds, right? So these things you should always have in mind, right? So firstly, we'll consider about alkenes. So alkenes are unsaturated hydrocarbon that contain one or more double bonds, right? So the carbons which are linked by carbon-carbon double bond are bound together by two bonds. So one bond is sigma and the other bond is pi. Also, you should know that whenever there is a double bond between carbon and carbon, so there is restricted rotation between carbon and carbon. So there is no free rotation around this carbon-carbon bond. As a result of this restricted rotation, we get cis and trans isomers, right? The hybridization of the carbon, which is doubly bonded, is sp2, and the bond angle is 120 degrees for alkenes. Now we have ethene. So ethene is commonly known as ethylene as well. So its general formula is C₂H₁. It's the simplest of alkenes, right? You cannot have one carbon alkene, so you can have at least alkene with the two carbons. So this is the simplest of alkenes, right? So the geometry is trigonal planar, right? The bond angle is 120 degree. Hybridization is sp2 hybridization, right? So similarly, we have propylene. So here we have structure of propylene. So you can see in propylene we have three carbons, and here we have carbon-carbon double bond. So just remember that only the carbon which are doubly bonded, they have sp2 hybridization. So this carbon is singly bonded. It has four carbon atoms. It has four bonds. So this is sp3 hybridized. However, this is sp2 hybridized. Here we have butene, right? So in case of butene, So the carbon-carbon double bond can be between carbon 1 and 2, and it can be between carbon 2 and 3. So here we have two isomers which are differing on the position of double bond, right? So we have, this is 1 butene and 2 butene. So the position isomers, they exist from this butene and onwards higher hydrocarbon. In case of lower hydrocarbons like propene and ethene, so this position isomers cannot exist, right? So just remember that in case of butene or higher alkenes, so this phenomenon of position isomer is observed, right? So there are many compounds which contain 2 or more than 2 double bonds, right? So if a compound contains 2 double bonds, it's called diene. If it has 3 double bonds, it's called triene, and so on. So if the 2 double bonds are separated by at least one saturated carbon, right, then in that case the 2 double bonds, they do not affect each other and they react independently, right? So bonds of this type are called isolated bond or unconjugated double bonds, right? So just suppose that we have this double bond, and you can see that this double bond is, and this double bond, this is separated by one sp3 hybridized carbon, right? So these 2 double bonds are separated by at least one saturated carbon, that is sp3 carbon. So these double bonds are called isolated or unconjugated. So when we carry out reaction, both will act independently. So this double bond will not influence this double bond. Right. So the term unconjugated double bond also includes cumulative double bonds. The cumulative double bonds are double bonds in which 2 double bonds are present with the same carbon. So you can see these are 2 double bonds and they are attached to the same carbon here, right? So such systems are called alkene. So this alkene is called alkene, right? Whenever there is a cumulative double bond, then such system will be called alkene. Right? So then we have third type of double bonds. So if 2 double bonds are separated by a single bond, right? These are not separated by a saturated carbon, these are separated by a single bond. So when 2 double bonds are separated by a single bond, such bonds are called conjugated bonds, right? So unconjugated alkenes show normal reactions of a double bond, whereas the conjugated alkenes show non-typical reaction. Why they show non-typical reaction? Because this double bond is affecting the reactivity of this double bond, right? So since these 2 double bonds are affecting each other, therefore the conjugated alkenes don't show normal reactions of an isolated double bond. So in general, alkenes are more reactive than alkanes because carbon-carbon double bond is a reactive functional group. So pi bond is a weaker bond and it can be easily broken, right? Sigma bond is a stronger bond, so it takes a lot of energy to break a sigma bond. However, pi bond can be easily broken. And pi bond is an electronically rich system, therefore pi bond will act as a nucleophile and it will react with electronically deficient reagents. So type of reactions which are undergone by the alkenes, these are 3 types: addition, combustion and polymerization. So the characteristic reaction which alkenes undergo is addition reaction. So in addition reaction, the pi bond is broken and pi bond is replaced by 2 sigma bond, right? For example, here we have a double bond here. So we add chlorine to it. So when chlorine is added, one of the pi bond will be broken and we'll get 2 sigma bonds. So you are getting 2 sigma bonds with this carbon and chlorine, and 1 pi bond has been broken. So in addition reaction, the hybridization of carbon changes. So here the hybridization is sp2, but in addition, so this result in formation of sp3 hybrid orbital, right? So in substitution reaction, there is no change in hybridization, but in case of addition reaction, there is a change in hybridization. Then we have combustion reactions. Combustion reactions, we burn the alkene such as ethene in presence of excess of air, and we get carbon dioxide plus water. And when ethene burns with sufficient of air, then it produces brilliant white flame, right? The combustion reaction is also reaction of alkenes. Furthermore, alkenes can undergo polymerization reactions by combining smaller molecules to form a larger molecule. For example, ethene can polymerize to form polyethylene, right? So this is polyethene, this is a polymer, and so suppose we use n number of molecules of ethene, so we will get the polymer in which we have n number of units of this. Now we have alkynes, right? The hydrocarbons with one or more triple bond are called alkynes. So they form another series of unsaturated hydrocarbons. So the two carbons which are joined by a triple bond, so the triple bond has one sigma bond and 2 pi bond. The hybridization will be sp, and the bond angle will be 180 degree, right? So alkynes are linear rod-shaped molecules because the bond angle is 180 degree. So because of this bond angle of 180 degree, the alkynes have linear rod-shaped geometry. Right, the simplest member of alkyne series is ethene. So this is ethene. So the molecular formula is C₂H₂. It's commonly known as acetylene, and the level structure is a linear molecule. You can see linear molecule. So the bond angle is 180 degree. You can see the linearity and the bond angle of 180 degree. So alkynes are of two types: terminal alkyne and non-terminal alkyne. Terminal alkyne is an alkyne in which there is at least one hydrogen directly bonded to a triple bond. So here I have a carbon-carbon triple bond, and here you have a hydrogen which is directly bonded to this triple bond. So if an alkyne has a hydrogen directly attached with a triple bond, then in that case this alkyne is known as terminal alkyne. In case if there is no hydrogen directly attached to this carbon-carbon triple bond, then in that case such alkyne is known as non-terminal alkyne, and they are also known as internal alkyne, right? So this is an internal alkyne because no hydrogen is directly attached with this sp hybridized carbon, right? It has been shown that terminal alkyne, just remember terminal alkyne must have at least one hydrogen directly attached to the triple bond. So when terminal alkynes react with strong bases like sodium metal or sodamide, then these form sodium acetylide, and hydrogen gas is liberated. So this reaction is showing that alkynes can undergo substitution reaction, right? Because this metal is substituting the hydrogen. Furthermore, this base has picked up this hydrogen. It means this hydrogen is acidic, right? So whenever a base reacts with a molecule and picks up a hydrogen, it means this hydrogen was acidic, therefore that's why the base has reacted with it. So this reaction of acetylene with sodium metal or sodamide indicates that alkynes are acidic, right? So why alkynes are acidic? Because they have the ability to lose hydrogen to form alkynyl ion, right? So it means that alkynes are proton donors, so it means they act as transited lauric acid. So these are proton donors, and since they are proton donors, therefore they act as acid, right? So they act as lauric-bronsted acid. So the triple bond is sp hybridized. So due to the s character, which is 50% in the alkynes, right? So this sp hybrid orbital exhibit higher electronegativity, right? And because of their high electronegativity, they attract the CH bond towards the center, right? So since the electrons are pulling from this hydrogen to the central carbon of the triple bond, then this hydrogen has decreased in electronic density, right? So as you know that ability of an atom to attract shear pair of electron to itself is called electronegativity. So in case of sp hybridized orbital, there is sort of electronegativity in this carbon, right? This carbon of the triple bond, it has the ability to attract the electronic density from this hydrogen. As a result, this hydrogen becomes electronically deficient and becomes more acidic, right? So because of the increased acidity of this hydrogen, it can be easily lost. So that's why we say that alkynes are acidic. But just remember that only terminal alkynes are acidic, because in case if you have non-terminal alkyne, there is no hydrogen directly attached to the carbon-carbon triple bond, so therefore the electronic density will not be withdrawn from the carbon, right? So this hydrogen cannot be lost easily. So it's very important for you to note that only the terminal alkynes are more acidic, right? In case of the alkanes and alkenes, since there is lesser S character, so S character is not much prominent in alkanes and alkenes, therefore they do not undergo these sort of reactions. So alkanes and alkenes are not acidic, so they do not react with metals to liberate hydrogen gas. So the general trend in acidity is this one. So if we have a terminal alkyne, so here we have terminal alkyne with hydrogen directly attached to the triple bond, so this is most acidic. Then we have next here is the double bond. So double bond is less acidic than triple bond, and then we have an alkene. Furthermore, you can also see the trend. So here we have substituted alkyne, right? So the general trend is if you have two acidic hydrogens, that has greater acidity. Then if you have only one acidic hydrogen, so this is terminal alkyne with two hydrogens, this is terminal alkyne with the one hydrogen. So the terminal alkyne with two hydrogens is more acidic than terminal alkyne with one hydrogen, and this is very acidic than terminal alkyne with no terminal hydrogen here, right? So this will be very less acidic, right? So this is more acidic, this one with one hydrogen will be less acidic, and this one with no hydrogen will be least acidic of all. The type of reactions which alkynes undergo are addition, substitution, and polymerization. So just like the alkynes, that's like the alkynes also undergo addition reaction. So since there are two pi bonds, so that's why the alkynes use twice the amount of reagent in addition reaction, right? So in case of alkene, you use one molecule of bromine to add one double bond, but here we have two pi bonds, therefore we will be requiring two molecules of bromine, right? So in case of alkynes, we have to use twice the amount of reagent in addition reaction. Also, since the addition reaction is going on, so the change in hybridization will be observed. So here we have hybridization as Sp, but in the product the hybridization is Sp3, right? So whenever there is addition reaction, a change in hybridization will be observed. In case of substitution reaction, only terminal alkynes can undergo substitution reaction. So in substitution reaction, the first step is removal of this proton by a base. So we'll get an alkene ion. This alkene ion will act as a nucleophile and will carry out the removal of a leaving group. So this alkene ion is acting as a nucleophile on this electron deficient carbon of the ethyl bromide. So resulting will be, we will overall substitute this hydrogen with this ethyl group, right? So the substitution reaction are only carried out by the terminal alkynes. Further, in substitution reaction there is no change in hybridization. So this carbon is Sp and this carbon remains Sp carbon in the substitution reaction. Next we have polymerization reactions. Just like alkynes also undergo polymerization reactions. So alkynes can form linear polymers or they can form cyclic molecules. For example, we can convert this alkyne into benzene by polymerization reaction. So this is the end of this lecture. I hope you have understood the comparison of reactivity and structure of the alkane, alkynes and alkenes well. So thanks for your attention.